Hello, so this is Transport 2, Exam 2, and we're looking at a problem where you have gas flowing down a pipe and you have liquid condensing inside and around it. Um, what we want to find is how many, right now, for the dimensional analysis, what we want is to find if our dimensionless numbers are correct and how many we need of them. What we're really looking for is I is equal to n minus r. This is the number of dimensional numbers that we need. N is the number of variables we'll have, and then r is the rank. And to be able to find r, what we need to do is we need to define our variables. So what we're going to have is we're going to have Kc, that's the mass transfer coefficient. We're going to have velocity, we're going to have density, we're going to have viscosity. Sorry, I'm a bit sick. And then we're also going to have mass flux coefficient, and then we're also going to have the diameter. And we can put the units above. So we're going to have, this is meters squared per second. This is just meters. This is kilograms per meter cubed. This is meters per second. This is meters per second. And then this is kilograms per meter second. So basically we need to create a matrix and we're going to code that to find the rank. You can do it without coding, but this isn't a linear algebra class, so it'd be a lot easier without doing it. So basically, like, the rules to the game are, like, if this doesn't have kilograms in it, then it's a 0. So you can just automatically put in the stuff that doesn't have zeros. So these two do, they have 1. They have, 1 kilogram. And if it was kilograms squared, then there would be a 2 here. So we can just play the game the whole time. 1, 1. If it's in the denominator, then it's negative. Negative 1, 0, 1. Oh, sorry. 2. Negative 1, 3. Okay. And the same thing for seconds. 0, negative 1, 0. Okay, so we know that the number of variables is 1, 2, 3, 4, 5, 6. Now all we need to do is find the rank. And to do that, we're going to do a little bit of coding. Okay, so now we can do the finding the rank. So first we're going to import numpy as np as always, and then we can make an array. Should have already pulled up. Okay, and that's our matrix of what we found before, and then we can simply just do np dot linear algebra dot matrix underscore rank of x. Alright, so we'll run it, and we find that our rank is equal to 3. So from that, we should have found that r is equal to 3, and that means that the number of dimensionless groups that we need is 3. So now what we're going to do is we're going to define our core groups, and these are going to be used when we do this pi kind of method, the Buckingham pi method, and basically. Yeah, so now we have to find 3 because that's the number that we found for I. That's the number of dimensionless groups that we need. So the core groups that we're going to use are Kc, velocity, and viscosity. So these two have the same units, so it's going to be a lot easier to be able to do this method. So we'll have Kc, velocity, and viscosity. And then we're going to multiply it by basically the remaining variables. So you have the mass diffusive coefficient, and then you have density, and then you also have the diameter, right? And then we do this for the rest of them also. Okay. So now we can do the whole thing over for pi 3 in the same way that we did it. So we did 3 is equal to viscosity, VAB, or no, sorry, mass diffusive coefficient, constant, D. Okay, make sure you guys can see that. Okay, so the same thing that we did before, we gotta put the units, and then we'll put mass, kilograms, and seconds. Okay, so it's kilograms per meter second, meter squared per second, and then kilogram per meter cubed, and then meters. All right, so we play the same game. We decided to name it DEF. Oh, sorry. Yeah, that's fine. DEF. Right. So yeah, starting here, we have -1, and then plus 2D, and then minus 3E, and then plus F, and that's all equal to 0. And then for kilograms, we have 1 plus E, and that's equal to 0, so we know that E is equal to -1. For seconds, we have -1 minus D, and that's all equal to 0. So, I know I still gotta do this. D is equal to -1. Okay, so D is equal to -1, E is equal to -1, and now we can put that back here. I'll erase this part. So you get -1 plus, it's negative, so you get -2, and then that's positive, so, and then plus F is equal to 0. So then you get F is equal to 0. Okay, so now we put that back into here. So we know this is pi 1, this is pi 2. So now we know that pi 3 is equal to the viscosity times the mass diffusive coefficient times density times the diameter, and then we put DEF. So we know that F is equal to 0, this is equal to -1, and this is equal to -1. So we have viscosity over D, and then over density. Okay, so what we know is that pi 1 is actually the Sherwin number, and then we know that pi 2 is the Pecklin number, PE, and then we know that pi 3 is Schmidt, right? Make sure I got that right. Okay, looks good. So what we were looking for was Schmidt, Sherwin, but we're looking for Reynolds. So we know that we're going to have to combine 2 of these to make Reynolds. So I'll save you the work. It's pi 2 over pi 3. So we can put, I'm gonna fall off the table. Okay. So we can put pi 2 over pi 3, right? I mean, we have to find a way to be able to equal Reynolds. So what we're going to do is it's the old keep, change, flip. And then this gets flipped. So d, and then density over the viscosity. I know it's hard to see. So basically these cancel out, and you're left with velocity, diameter over viscosity. And that's all equal to the Reynolds number. So we found a relationship between all three of them, and we realized that those are the three that we need. So now we're going to do a little bit of coding to try to finish the problem. Okay, so we're going to start the coding part of this problem. Basically what we're going to do is we're going to create 100 data points and create a graph out of that, and yeah, so let's go ahead and get started. So first we're gonna import all of our necessary things. We've done this every single time. Import. Okay. Plots. Okay. And yeah, so we're gonna use, of course, we're gonna use NP, not P, for majority of things. We're gonna use minimize to minimize our error, and then the subplots and the rest of the stuff are just for plotting the actual graph. Okay. So yeah, yeah, all of those things are, well, obviously, and these things are just to make the subplot. It'll make a little bit more sense when we use them. So first, we have to create random variables for our Reynolds number and our Schmidt number, and then our Sherwin number will be based off of that. So let's see, random dot uniform, and then we were already given parameters in the problem, and then we need 100 points. So these are the parameters that we were given in the problem. And the same thing for the Schmidt number. We have, it should be 0.5 and 2.5, I believe. Random dot uniform. It should be 0.5 and 2.5. 2.5. And we need 100. Okay. That would be near me, right? Okay, so then for the Sherwin number, what we need to do is take those random numbers that we just created and put it into the formula times 0.083 and all of that to four, I think. Yeah, that looks right. Okay. So, and then we have to actually create the our error parameters. So it should be given 10% across the the normal distribution. So it should be random dot normal, and then it'll be that it's yeah, I think that's right. Okay, looks good. So now well, so that's creating 100 um, data points um, for our Reynolds number, Schmidt number, and our Sherwin number. So now what we need to do is, one, we need to take the log of both sides, and then once we take the log of both sides, we need to make sure that they're all in the same, I'm gonna say dimensions, but it's not actually dimensions. They make sure that they're in the same like amount of numbers, list of numbers, um, and one way that we can do that is column stack, and then it's, I always forget this one, ones underscore like, and then we're going to take the log of the Reynolds number, and then we're going to take the log of Schmidt. It's a lot of parentheses. Okay. So then what we need to do next is basically, so since we took, we need to make sure that those parameters are exact. So what we can do is we can multiply it by the transpose of both sides, and I'll show you how to do that. It's np times linear algebra dot inverse. Yeah, and then to reverse that, you gotta take the inverse of it. So it should be t at x, and then another at sign, x dot t, and p dot log. Okay. So then we can check it by setting it back, since we logged it, of, it should be the initial value. Try it though. We got an error. Is that because I didn't run them all at the same time? Okay. So let's look. Column stack. So that closes that one, and then we should have, cool. I'll have to restart this whole thing. What about that? Alright, there we go. So now we have values in the array. Sorry, I've done this too many times. We've been making stupid errors. So there's the values of the array, and that's the first value in B. We don't actually need that. That's fine. So now we can make, we have created our initial values for our error. It's 10%. But we can create a function of p, and then we're going to want to return the sum of the function, or sum of the error, showing minus, what was the p? Okay. The first one times the Reynolds number, all up to p, the second value times Schmidt times, it should be raised to the power of the third, and then that whole thing should be squared. Okay. Cool. Make sure I don't have any errors. Okay, good to go. Okay, so now we want to, I guess I can put that here. So now we want to minimize that error. Minimize. And we're going to have to put in the values that we initially had. So 0.023, 0.83, and then 83, and then what was that last one? 0.44. Okay, so that should be good. Okay, cool. So okay, cool. So now what we want to do is we want to go ahead and create our figure. So it should be figured make underscore subplots. No, we don't have to put anything in it. And then we're gonna actually start putting stuff in our figure. So trace, and this is pretty cool. The 3D. So now we're just setting what we want in it. So we want x to be equal to the Reynolds, y to obviously be equal to the Schmidt, z is equal to Sherman, and then we can make, the mode is equal to markers, and then the marker size is equal to 3, and then marker color is equal to Schmidt. Okay, so that should be good. Let me run that. That was a long. Let's see what I have. Okay, gotcha. So I forgot one. Import plotly graph underscore object as go. Okay, so we're good. I put these in parentheses for some reason. So now we made our subplot. So now we can make the grid, and this one's a little bit complicated. It's np dot mesh grid. Keep it on one space. and then we have those values from before. It was, what was it? Actually, I think I'm gonna have to go up in about 30. I think it was 35,000. Yeah, slip number in. Okay, 35 to 3, and then we can just do 20. That should be enough. Okay, and then the same thing for the Schmidt number. So we have what is it? 0.6 and then 2.5. No, it should be 0.5, I think. 2.6 and then 20. Okay. So now for the grid, for the Sherman grid, we have to do the same thing, but since we took the ln of both sides before, we have to use the exponential of those values in the array. So it should be the exponential of b, the initial value, times re grid, times the 1 times sc grid times b2. Okay. So then we can create a different variables for RE and actually for all three of them. I'm just going to put, I guess, an N in front of them and make it a little bit easier. And CH and C NCH in zip, and that would be RE grid, C grid, and SH grid. Okay. So yeah, so for that one, what we want to do is we want to create lines for all of them. So then we can config dot add underscore trace, and it'll be kind of the same process. Go dot scatter 3D, and then it's the same stuff. So x is equal to nre, y is equal to n. There you go. N Schmidt, and then z is equal to nch. Okay, and then the mode here. I'm gonna stop cutting myself. The mode here would be lines, and then we can make the line color. I can see it. Line color. Sorry, my screen has a lot of stuff on it right now. Line color is equal to gray. Okay. So, and then we should be able to copy and paste that whole thing from here and just replace the Reynolds and the Schmidt right here. And then replace these parameters with each other. Okay. So then, let me, before I move on, let me make sure I don't have any errors. That was a lot. Invalid syntax. Okay, so I forgot. I don't know why I didn't see that in the first place. Okay. As long as it runs. Okay, so now what we're going to do is we're going to update the layout. It should just be underscore layout. Images, I don't know images. And then the width will be 800. The height will be 800. And then the we can create the scene, and that's equal to dict x dot, or I guess it's just x-axis underscore title is equal to re, and then y-axis title axis underscore title is equal to sc, and then z-axis title is going to be equal to ch. Alright, so let's run it. Alright, perfect. So here's what we get. Okay, there we go. So now we get a graph of scatter plots on a plane. That's what we're looking for. Thank you very much.